Hi, my curious fellows. Welcome back to Hafee Sleep. I'm so glad you're here. Whether you're curled up under blankets, sipping late-night tea, or just letting the world fade away. Welcome to Hafee Sleep. Tonight we're diving into one of the universe's quietest secrets, a discovery so profound it explains why you even exist. It's the story of an invisible force field that gives weight to everything, from stars to your fingertips, and the ghostly particle that proved it's real. Before we begin, if this soothes your mind or sparks your curiosity, subscribe for more journeys into science, space, and serenity. Comment below where you're watching from. I love imagining you all across the globe, from Tokyo nights to Paris dawns. Give this video a like if you're ready to unwind with me. Now, close your eyes if you'd like. Breathe slowly. Let's wander through the cosmos together. Because tonight, we will meet the particle that made the universe sticky and is unwantedly called the God's particle. Ready? Let's begin. This isn't just another subatomic speck. It's the key to understanding why stuff has stuffness. Why don't you float away? Why stars burn and galaxies spin? Buckle up, because we're diving deep into the quantum soup to uncover the story of the Higgs Boson, what it is, how we found it, why it got that dramatic nickname, and why its discovery was one of the loudest cheers in the history of human curiosity. So let's start with the big question. What is the Higgs boson? To get there, we need to rewind our thinking. Forget solid objects for a moment. Imagine everything in the universe, you, me, the air, distant stars, is made of incredibly tiny building blocks called fundamental particles. Think of them as the ultimate Lego bricks. For decades, physicists had a remarkably successful theory called the Standard Model that described almost all these particles and the forces that govern how they interact. Electrons, quarks, which make up protons and neutrons inside atoms, photons, particles of light, and others. They were all accounted for, and the theory predicted their behaviors with stunning accuracy. But there was a colossal problem lurking in the math. A problem so big it threatened to bring the whole elegant structure crashing down. Mass. The Standard Model. Think of it as the ultimate Lego instruction manual for building the universe. For decades, physicists meticulously sorted all the tiny, fundamental bricks, the quarks that make up protons and neutrons, the electrons buzzing around them, the ghostly neutrinos, and the force carriers, like the photon, the particle of light. And the instructions? They were these incredibly beautiful, powerful equations that described how these bricks snap together, how they interact, governed by fundamental forces. It worked astonishingly well, like building a magnificent, intricate castle. Most of the walls stood straight, the towers reached high, and the drawbridge worked. Now, the forces. This is where the Standard Model truly shone. It described 3 of the 4 fundamental forces of nature with breathtaking precision. First, electromagnetism. This is the force behind pretty much everything we experience directly. Light, radio waves, the electricity powering your device, the magnetism holding a note on your fridge, and crucially, the force that holds electrons to atomic nuclei, making atoms possible. How does it work? Imagine 2 ice skaters gliding smoothly on a perfectly frictionless rink. They want to interact, to change each other's path. How? They start tossing a ball back and forth. Every time one throws the ball, they recoil backwards a bit. Every time the other catches it, they get pushed. This constant exchange of the ball makes their paths curve towards each other or veer away, depending on whether they're attracting or repelling. In electromagnetism, the ball is the photon. Electrically charged particles, like protons and electrons, are the skaters. They attract or repel by constantly exchanging these tiny massless packets of light energy, photons. Because the photon is massless, it can zip across vast distances at the speed of light, making electromagnetism a powerful long-range force. The equations describing this are elegant, symmetrical, and work perfectly. Then there's the strong nuclear force. This is the ultimate superglue. Protons are all positively charged and crammed incredibly close together in an atom's nucleus. Electromagnetism hates this, like charges repel. They should explode apart violently, but they don't. Why? Because the strong force is about 100 times stronger than electromagnetism at these tiny distances. It overpowers the repulsion and binds the protons and neutrons together. Think of our skaters again, but now they're stuck together in a mosh pit. The balls they exchange here are called gluons. Quarks, the particles inside protons and neutrons, constantly exchange gluons. Gluons are also massless, like photons. But there's a crucial difference. Gluons themselves carry the color charge, a property analogous to electric charge but for the strong force. And this creates a bizarre effect. Instead of the force getting weaker with distance like electromagnetism, the strong force actually gets stronger. The farther you try to pull quarks apart, it's like stretching an incredibly tough rubber band. This is why you never find a lone quark in nature. They're always tightly bound inside particles like protons and neutrons. The standard model equations for the strong force, called quantum chromodynamics or QCD, are complex, but they work brilliantly, explaining how atomic nuclei hold together. Now enter the weak nuclear force. This force is crucial, but operates more behind the scenes. It's responsible for certain types of radioactivity, like beta decay, where a neutron turns into a proton, or vice versa, inside a nucleus, spitting out an electron and an antineutrino. It's also vital for the nuclear reactions that power the sun, turning hydrogen into helium. Without the weak force, stars wouldn't shine. So clearly, it's fundamental. The skaters involved here are particles like quarks and leptons, electrons, neutrinos. The balls they exchange are particles called the W boson, which comes in positive and negative versions, W plus and W, and the Higgs boson. Here's where the beautiful Lego castle starts to develop a worrying crack. Remember how the photon and gluon are massless? The elegant mathematical structure of the standard model, the very symmetry that made it so powerful and predictive for electromagnetism and the strong force, insisted that the W and Z bosons must also be massless. The equations demanded it for the whole theoretical framework to hang together consistently. Symmetry in physics often means that the laws look the same under certain transformations, like rotating your view or swapping particles. The symmetry underlying the combined electromagnetic and weak forces, called electroweak symmetry, was mathematically stunning. It unified them into a single, elegant framework at very high energies, like those just after the Big Bang. But reality stubbornly refused to cooperate. Experiments screamed a different story. We knew the W and Z bosons were heavy, seriously heavy. While a massless photon zips around effortlessly, the W boson weighs in at about 80 times the mass of a proton, and the Z boson is even heavier, about 90 times a proton's mass. That's not just a little chubby. That's a sumo wrestler compared to a featherweight photon. This was a massive problem, pun intended. It was like the Lego manual showing a picture of a sleek racing car, but insisting you must use giant, square wheels made of lead. The design looked perfect on paper, but if you tried to build it according to the instructions, the car wouldn't just be slow, it wouldn't move at all. The beautiful symmetry was broken in our everyday, lower energy world. Why was this mass such a disaster? Think about the skaters tossing the ball. If the ball, the force carrier, is incredibly heavy, like a cannonball, what happens? The skaters can barely lift it. They can only toss it a tiny, tiny distance. That means the force it carries has an extremely short range. And that's exactly what we see with the weak force. While electromagnetism reaches across galaxies, thanks to massless photons, the weak force only works over distances tinier than the size of a proton. It's incredibly short range. The Standard Model could incorporate massive force carriers mathematically, but doing so in a naive way completely destroyed the beautiful, predictive power and the underlying symmetry that made the model work so well for the other forces. It made calculations blow up into nonsensical infinities. The theory became mathematically inconsistent and ugly. The crack in the castle wall threatened to bring the whole structure down. This presented a profound puzzle. Why do some particles have mass? And specifically, why do the W and Z bosons have so much mass, utterly defying the symmetrical elegance of the electroweak theory? Electrons have a little mass. The quarks that make up protons and neutrons have varying masses. The top quark is enormously heavy, while the up quark is relatively light. Neutrinos have almost incomprehensibly tiny masses. Photons and gluons have none. Where does this mass come from? What determines how much mass each particle gets? The Standard Model, as originally formulated, had absolutely no answer. Mass was just a number plugged in by hand for each particle, like an arbitrary sticker price with no explanation of the cost. It was deeply unsatisfying. The theory could describe what particles did, but not why. They had the fundamental property that allows them to be stuff rather than ethereal energy zipping around. This is where the plot thickens, and the missing piece wasn't another Lego brick, not another particle to add to the list. The solution required a shift in perspective, a fundamental change in how we imagine the fabric of reality itself. Physicists realized the missing ingredient wasn't a thing, but a stage upon which all things play. It was a field. We're used to fields. Think about a magnetic field. You can't see it, but you know it's there when iron filings suddenly line up around a magnet, or a gravitational field. You feel it every time you jump and come back down. It holds planets in orbit. These are invisible influences permeating space, affecting things within them. The revolutionary idea proposed in the mid-1960s by several brilliant minds, Peter Higgs, François Englert, and Robert Brute, and independently by Gerald Guralnick, C.R. Hagen, and Tom Kibble, was that the entire universe is filled with another kind of field, an invisible molasses-like entity now called the Bohm-Higgs field. Unlike gravity or magnetism, which gets stronger near sources, like a planet or a magnet, the Higgs field is believed to be constant and uniform throughout the entire universe, even in the deepest, emptiest void of space. It's always there, everywhere. But how could a field give particles mass? This is where the ingenious concept of spontaneous symmetry breaking comes in, and it's best understood with our crowded room analogy. Imagine that grand symmetrical banquet hall again. It's vast, perfectly circular, with people representing the Higgs field milling about randomly, completely evenly distributed. There's perfect symmetry. No direction is special. Now, a famous scientist, let's keep it as Einstein, walks into the room. Suddenly, that perfect symmetry is broken. People cluster around Einstein. They want autographs, to ask questions. It creates a crowd. Now, moving through this room depends on who you are. If you're another famous scientist, you might also attract a crowd, making it hard to move. You experience a lot of drag. If you're a lesser-known physicist, you might slip through the crowd with only a little resistance. If you're a complete unknown, like a photon just trying to deliver a message, you might zip through the crowd entirely unnoticed, feeling no drag at all. Now translate this back to fundamental particles moving through the universe, which is filled with the constant uniform Higgs field. The more a particle interacts with the Higgs field, the more drag it experiences, the more mass it has. Particles like the top quark interact very strongly. They are the Einsteins, trudging slowly, feeling heavy. Particles like the electron interact moderately. They have some mass. Neutrinos interact incredibly weakly. They have almost no mass, slipping through almost effortlessly. Photons and gluons. They don't interact with the Higgs field at all. They are the perfect unknowns zipping through the crowd at the speed of light, completely massless. What about our troublesome W and Z bosons? They interact very strongly with the Higgs field. They are like celebrities trying to cross a room filled with eager fans. They experience massive drag, hence their large masses. This beautifully explains why they are heavy while photons are massless, all within the framework of the electroweak theory. How? The presence of the Higgs field breaks the electroweak symmetry spontaneously as the universe cooled after the Big Bang. At those ultra-high energies, symmetry was restored. The Higgs field wasn't active in the same way, and the W, Z, and photon were all massless components of a unified electroweak force. As the universe expanded and cooled, the Higgs field condensed, like steam turning to water, filling space. This broke the symmetry, giving distinct identities to the photon, which remained massless, and the WZ bosons, which became massive. The Higgs mechanism didn't just patch the crack, it revealed a whole new layer of the castle's foundation, making the structure stronger and more beautiful than ever. So the missing piece wasn't a particle you could necessarily bump into directly. It was this pervasive, invisible cosmic treacle, the Higgs field, that selectively slows down certain particles, giving them the property we call mass. It's the reason the universe isn't just a blinding flash of massless energy zipping around forever. It's the reason matter has substance, can clump together, and allows atoms, planets, stars, and curious physicists to exist. The field was the key. But to prove it existed, we needed to find its signature, its telltale ripple, the particle that bears its name, the Higgs boson. But that, my friend, is a story of its own, one involving tunnels deep underground, giant magnets colder than outer space, and a hunt spanning half a century. The discovery of the field's signature particle would become one of humanity's greatest scientific triumphs. Ah, yes, finding it. The Higgs boson wasn't just hiding, it was playing the ultimate game of cosmic hide-and-seek with rules stacked absurdly in its favor. Imagine trying to find a single, incredibly specific snowflake that only exists for a trillionth of a blink of an eye, somewhere in the middle of a raging blizzard. And the only way to make that snowflake appear is to smash two entire icebergs together with such force they momentarily turn back into primordial steam. That was the scale of the challenge. Let's unpack why it was so monumentally tricky and how humanity rose to meet it with the most audacious machine ever conceived. First, The Higgs boson itself. Remember, it's not a stable brick in the universe's Lego set. It's a ripple, a fleeting vibration in the ever-present Higgs field. Think of it like plucking a guitar string. The note rings out, but it fades almost instantly. The Higgs boson is that note, but vanishingly faster. Its predicted lifetime, about 1/10 sextillionth of a second. That's 0.01 seconds. In that incomprehensibly brief flash, it must decay, transforming into other, more stable particles. You don't see the Higgs directly. You see its children, its grandchildren, the debris of its instantaneous decay. It's like trying to identify a rare, exotic bird solely by finding a few unique feathers scattered after it exploded mid-flight. You have to piece together the identity of the parent from the fragments. Second, its mass. While massive by particle standards sounds abstract, think of it this way. Energy and mass are two sides of the same coin. Thank you, Einstein. To create a heavy particle, you need to concentrate a lot of energy into a vanishingly small point. The Higgs boson, predicted to be around 100-200 times heavier than a proton, required energies far beyond what any previous particle collider could muster. It was like needing a cannon to launch a bowling ball to the moon when all we had were slingshots. So, how do you recreate the conditions needed to make this ghost appear? You need energy. Immense, concentrated energy. The universe itself provides the blueprint. Just after the Big Bang, the cosmos was unimaginably hot and dense, a seething soup of pure energy, where particles like the Higgs boson popped in and out of existence constantly. To see the Higgs, we needed to turn back the cosmic clock, recreating a tiny speck of that primordial fury here and now. Enter Einstein's E=mc square again. If you smash two particles together with enough speed, the colossal kinetic energy packed into that collision can spontaneously convert into mass, new particles. The faster they go, the more energy available to conjure heavier particles. It's the ultimate alchemy, speed turning into matter. And the fastest things we know? Particles accelerated to near light speed. Protons became the projectile of choice. Why protons? They're relatively heavy, for fundamental particles anyway, though they're made of quarks, positively charged, so we can steer them with magnets, and readily available. Strip the electrons off hydrogen atoms and you've got protons. We wouldn't smash whole atoms, too messy. We'd strip protons naked and hurl them at each other. To make is this impossible possible, the engineers present you the ultimate machine, the Large Hadron Collider, or LHC. The vision was breathtakingly simple and impossibly complex. Build a racetrack, a very, very big racetrack. Accelerate two beams of protons in opposite directions to 99.9999% of the speed of light. Focus them into hair-thin streams. Smash them head-on with cataclysmic force. Then build unimaginably complex detectors around the collision points to catch the subatomic shrapnel. Do this billions of times per second. Sift through the resulting data avalanche. Hope to find the faintest whisper of a ghost. To make this happen, let's dig a perfectly circular tunnel deep enough underground, about 100 meters, to be shielded from cosmic rays and Earth's tremors. Make it 27 kilometers, 17 miles long, so big you could fit the entire Circle Line of the London Underground inside it with room to spare. This colossal ring, straddling the Swiss-French border near Geneva, is the foundation. Building it required tunneling through varying rock strata, managing groundwater, and maintaining precision alignment over its entire length. A civil engineering marvel. The cold heart. To steer and focus the proton beams, you need incredibly powerful magnetic fields. Enter superconducting electromagnets. These are special magnets that, when cooled to unbelievably low temperatures, lose all electrical resistance, allowing massive electrical currents to flow without energy loss, generating immense magnetic fields. How cold? 271.3. Colder than the void of outer space. Achieving this requires a vast, distributed cryogenic system pumping liquid helium through pipes surrounding the magnets. It's the largest refrigerator on the planet, maintaining a section of the tunnel colder than any natural place in the known universe. If this system fails, the magnets quench, suddenly losing superconductivity, releasing their stored energy violently, like an explosion. Keeping this icy heart beating is a constant ballet of precision engineering. Accelerating the beams. Protons don't start at near light speed. They begin their journey in a small, linear accelerator, getting an initial kick. Then they're fed into a series of smaller circular accelerators, like booster stages on a rocket, each one increasing their speed and energy. Finally, they're injected into the mighty LHC ring. Here, powerful radio frequency cavities, like synchronized kicks, give the protons precise boosts of energy every time they zoom past, accelerating them gradually over millions of laps. Think of pushing a child on a swing. A tiny push at just the right moment each time they swing by adds up to big height. After about 20 minutes, each proton beam is humming along at 99.99999% of light speed, carrying the energy of a freight train in a single microscopic particle. Each beam contains hundreds of billions of protons packed into thousands of ultra-dense bunches. The collision points. Getting two beams traveling in opposite directions at near light speed to collide head-on is like firing two needles from across the Atlantic Ocean and making them hit precisely point-to-point, mid-ocean. Powerful superconducting quadrupole magnets focus the beams down to a width thinner than a human hair. At 4 points around the ring, the beams are steered to cross paths. When two proton bunches meet, hundreds of protons actually collide simultaneously within a space smaller than a single atom. The energy density at these microscopic impact points is staggering, comparable to the state of the universe just a trillionth of a second after the Big Bang. Bang. Mini creation events, billions of times per second during operation. This is where the magic and the Higgs Boson might appear. The ultimate digital cameras, Atlas and CMS. Creating potential Higgs bosons is only half the battle. You have to see them decay. Remember, they vanish instantly into a spray of other particles. Surrounding the 4 collision points are gigantic detectors, each a unique masterpiece of scientific collaboration. Atlas, a toroidal LHC apparatus, and CMS, compact muon solenoid, are the 2 general-purpose workhorses designed specifically for the Higgs hunt. Imagine building cathedral-sized, multi-layered, ultra-high-speed digital cameras, but instead of capturing light, they capture everything that bursts out from the proton collisions. Think of these detectors like giant spherical onions, each layer designed to catch different types of particles and measure their properties: path, energy, electric charge, type. Closest to the collision point, a maze of ultra-precise silicon sensors. Charged particles, like electrons or protons, zip through these, knocking electrons loose as they pass. This creates tiny electrical signals, allowing scientists to reconstruct the particle's path with pinpoint accuracy, like tracing the vapor trail of a jet. This reveals the particle's trajectory and charge. Outside the tracker lie layers designed to stop particles and absorb their energy. Electromagnetic calorimeters measure the energy of electrons, photons, and other light particles. Hadronic calorimeters measure the energy of protons, neutrons, pions, and other particles made of quarks. They work like super sophisticated, segmented stopping blocks. When a particle slams into the dense material, lead, iron, it creates a shower of secondary particles. The total energy deposited in the shower is measured, telling us the original particle's energy. It's like catching a bullet in ballistic gel. The depth and spread of the damage tell you the bullet's energy. The muon system. Muons are like heavy, penetrating cousins of electrons. They pass through the inner layers like bullets through tissue paper. So, the outermost layer is a vast array of detectors embedded in the iron yoke of the magnet itself. More on that next. Specifically designed to catch these elusive particles and trace their paths. Magnetic mines. Both Atlas and CMS have incredibly powerful magnets built right into them. Why? To bend the paths of charged particles. A charged particle moving through a magnetic field curves. The amount of curvature tells you the particle's momentum, mass times velocity. Stronger magnets mean tighter curves, allowing for more precise momentum measurements. CMS uses a giant superconducting solenoid magnet, generating a field 100,000 times stronger than Earth's. Atlas uses a unique toroidal, donut-shaped, magnet system. These magnets are engineering feats in themselves, generating immense forces that the detector structures must withstand. Each collision of proton in the Large Hadron Collider produces hundreds of particles flying outwards. Each layer of the detector generates signals. Millions of sensors are read out every time bunches cross paths, which happens 40 million times per second. The total data flow is mind-boggling. Petabytes per second. Millions of gigabytes. It's an impossible fire hose of information. So, sophisticated trigger systems act like super-fast editors, instantly analyzing the signals and deciding in microseconds whether a particular collision looks interesting enough, like it might contain a Higgs decay signature, to warrant saving the full data. Even with this ruthless filtering, the LHC experiments generate enough data each year to fill a stack of DVDs reaching to the moon. Handling this requires massive global computing grids, the LHC computing grid, a network of hundreds of thousands of computers worldwide, crunching the data around the clock. The needle in the haystack, spotting the Higgs. So, protons collide at near light speed inside the collider. For a fleeting instant, the energy is so intense it can create a Higgs boson. The Higgs instantly decays, remember, 1/10^60th of a second, into a specific combination of lighter, more stable particles predicted by theory. Common decay paths include 2 high-energy photons, gamma rays, 2 Z bosons, which then decay further, e.g., into 4 charged leptons like electrons or muons, 2 W bosons, decaying, e.g., into leptons and neutrinos. Bottom quark and anti-bottom quark pair, B and B bar, Atlas and CMS don't see a Higgs boson decay. They see the end products, a spray of photons, electrons, muons, quark jets, sprays of particles from quarks like bottom quarks. The challenge? These exact same sprays of particles can be produced by countless other, much more common processes happening in the proton collisions. The Higgs boson signal isn't a bright, unique flare. It's a tiny, specific excess of events with certain particle combinations at a particular combined energy, mass, buried under a mountain of look-alike background noise. Imagine you're listening for a rare bird's call in a dense rainforest teeming with insect noise, monkey howls, and other bird songs. The rare bird has a very specific two-note call. You record everything, Then you meticulously analyze hours and hours of recordings, counting how many times you hear that specific two-note sequence. But you know that sometimes, just by random chance, two other birds might sing notes that accidentally mimic the rare call. To be sure you've really heard the rare bird, you need to hear its specific call significantly more often than you'd expect from random background noise alone. That's the essence of the Higgs hunt. Scientists spent years calculating precisely what the background, the imitators, should look like for every possible decay channel, based on the well-understood standard model processes, without the Higgs. Scientists recorded billions of actual collisions and sorting the events into categories based on what particles they produced, e.g., events with 2 photons, events with 4 high-energy muons, events with bottom quark jets. And then, for each category, they plotted the combined energy, or invariant mass, of the detected particles. If the Higgs boson, say with a mass of 125 GeV, decays into 2 photons, the combined energy of those 2 photons should cluster around 125 GeV. If it decays into 4 muons via 2 Z bosons, the combined mass of the 4 muons should cluster around 125 GeV. In all of these mountains of data, scientists were looking for a small bump or excess of events piled up at a specific energy, mass, in these plots, above the smoothly falling background predicted by the non-Higgs processes, determining if the bump is statistically significant. Particle physics demands extremely high standards for a discovery. We don't say eureka for a hunch. We require the signal to have a significance of at least 5 sigma. What does that mean? It means there's less than a 1 in 3.5 million chance that the bump is just a random fluctuation of the background noise. It's like being so sure about that rare bird call that you'd bet your life savings on it being real, knowing the odds of being fooled by random noise are astronomically tiny. Achieving 5 sigma takes an enormous amount of data and painstakingly eliminating systematic errors. The LHC started its incredible journey by colliding protons in 2009. The hunt was on. Years passed. Mountains of data grew. Thousands of scientists on ATLAS and CMS worked tirelessly, independently analyzing the data, double-checking calibrations, refining techniques, searching for the bump. The tension was electric. Rumors flew. Was there a hint around 125 GeV, or 140, or nowhere? Slowly, cautiously, bumps began to emerge. First tentative hints, not yet significant. But as more data poured in, the bump around 125 GeV grew taller and sharper, particularly in the 2-photon and 4-lepton channels. By late 2011 and early 2012, the whispers became a murmur, then a shout within the collaboration. The significance climbed, 3 sigma, 4 sigma. The background stubbornly refused to mimic this persistent bump. Finally, on July 4, 2012, in a packed auditorium at CERN and broadcast live to the world, the spokespersons of ATLAS and CMS presented their results. The graphs were unmistakable. Clear peaks stood tall above the background curves at 125-126 GeV. The combined significance? Over 5 sigmas for both experiments independently. The Higgs boson, the capstone of the standard model, the signature of the field that gives mass to the universe, had been found. Peter Higgs, then 83, wiped away a tear. François Englert, Robert Brout had passed away, beamed. The decades-long quest, involving generations of theorists and experimentalists, billions of dollars, and unprecedented engineering, had reached its triumphant climax. The ghost had been captured, not in a jar, but in the irrefutable language of data and statistics. The universe had yielded one of its deepest secrets. The cosmic campfire's spark had been glimpsed. And the cheering wasn't just in that room. It echoed through the entire scientific world and beyond, a celebration of human curiosity and ingenuity at its absolute peak. The discovery wasn't the end, though. It was the key turning in the lock, opening the door to even deeper questions. You know, we throw around words like monumental and Nobel Prize, almost casually sometimes, but when it comes to finding the Higgs boson, those words barely scratch the surface. It wasn't just a discovery. It was like finally finding the master key to a vast, intricate mansion we'd been living in for decades, exploring room by room, but never quite understanding how the whole structure stood up. Imagine building a magnificent clock, every gear perfectly shaped, every spring tensioned just so, and it ticks beautifully. But you have no idea why the mainspring holds its energy. Finding the Higgs was discovering the physics of that spring. It answered a question so fundamental, so woven into the fabric of our existence, that we often forget to even ask it. Why is there stuff instead of just light? Let's really unpack why finding Higgs boson was such a cosmic scale big deal, layer by layer, starting right at the foundation of our understanding of reality itself. The discovery of Higgs boson was the capstone for completing the grand blueprint presented by the Standard Model. Think of the Standard Model as the ultimate IKEA manual for building the universe. For over half a century, physicists worldwide had been meticulously assembling this incredible intellectual furniture. Through Standard Model, they identified all the pieces. This includes the matter particles called fermions, like the legs, shelves, and screws. These are the quarks, building blocks of protons and neutrons, the electrons, and their quirky cousins like neutrinos and muons. 6 types of quarks, 6 types of leptons, including the electron, the fundamental stuff. Then comes the force carriers called bosons, like the glue, the brackets, the instructions for assembly. The photon, carrying electromagnetism. The gluon, carrying the strong nuclear force, gluing quarks together. And the W and Z bosons, carrying the weak nuclear force responsible for radioactivity and sunshine. And the instructions? Beautiful, powerful equations. Quantum electrodynamics, QED, for electromagnetism. Quantum chromodynamics, QCD, for the strong force. And the electro-weak theory unifying electromagnetism and the weak force. This manual was stunningly successful. It predicted the existence of particles before. We found them, like the charm quark, the W and Z bosons. It explained chemical bonds, nuclear reactions, why light behaves the way it does, with mind-boggling precision. It was like building the Billy bookcase of the cosmos, and it stood straight and held books perfectly, except for one nagging central flaw. The instructions demanded that the force carriers, especially the W and Z bosons, should be massless, like the photon, but experiments screamed they were heavy. Imagine the IKEA manual insisting you use helium balloons as shelf supports. They'd float away. The whole elegant structure, while mostly built, wobbled precariously on this inconsistency. The Higgs mechanism, and crucially, the Higgs boson as its proof, was the one missing piece. The specific, uniquely shaped bracket needed to secure the entire assembly. Finding it wasn't just adding another shelf, it was placing the final critical support that locked the whole magnificent edifice into place, proving the blueprint was fundamentally sound. It validated decades of theoretical and experimental work. It showed us, yes, we are on the right track. We understand the basic rules governing almost everything we see. That's Nobel Prize territory number 1, confirming the most successful scientific theory ever devised. The second significance of finding Higgs boson was the explanation of mass. This is where it gets personal. Forget distant galaxies for a second. Look at your hand. Feel the weight of your phone. Inhale. That solidity, that tangibility, that very existence of matter as we know it, it hinges critically on the Higgs field. Think back to the cosmic campfire. The Higgs field is like that pervasive warmth, but instead of heat, it imparts resistance, mass. Without it, the universe would be a vastly different, utterly lifeless place. If electrons had no mass, like photons, they couldn't orbit atomic nuclei. They'd zip away at light speed the moment they were near a proton. Poof, no atoms. Forget hydrogen, forget oxygen, forget carbon. The basic building blocks of everything, gone. No electrons, no atoms. No atoms, no molecules, no molecules, no chemistry, no DNA, no water, no proteins. Just a chaotic soup of fundamental particles whizzing around independently at light speed. No structure, no complexity. A universe of pure, formless energy. Even if protons and neutrons somehow formed without atoms, which the Higgs also affects via their quark constituents, they wouldn't clump together. Gravity relies on mass to pull things together. With no mass, or vastly different masses, gravity couldn't form stars from gas clouds. No stars, no planets, no heat, no light beyond the initial Big Bang flash. A dark, cold, empty void. No atoms, no molecules, no planets. Obviously no you, no me, no curious minds to ponder any of this. The Higgs field is the cosmic anchor. It's the reason particles experience inertia, resistance to changing their motion. It's why you can't push a stalled car instantly to highway speeds. It has mass inertia, and why you need brakes to stop it. This drag, imposed by the Higgs field, is mass for fundamental particles. It slows things down enough for them to interact, bind, and form complex structures. It makes the universe sticky. It transforms a blinding flash of pure energy into a place where matter can coalesce, stars can ignite, planets can form, and life can evolve. It answers the profound, almost childlike question, why doesn't everything just fly apart at light speed? That fundamental answer, the origin of mass for the particles that make up everything tangible, is Nobel Prize territory number 2. It explains the very fabric of our material existence. The third thing that the discovery of Higgs boson made is the unification of electroweak forces. Imagine looking at a picture of yourself as a baby, then as a teenager, then as an adult. You look different, but it's the same person. Forces in the universe have a similar history. The Higgs discovery gave us a crucial snapshot from the universe's fiery infancy. We experience 4 fundamental forces today: gravity, electromagnetism, EM, the strong nuclear force, and the weak nuclear force. The Standard Model brilliantly unified EM and the weak force into a single electroweak force, but only for the ultra-high energy conditions of the very early universe. Think of EM and the weak force as identical twins at birth. As the universe expanded and cooled, like growing up, they underwent a dramatic change. They split into the distinct forces we recognize today. The trigger for this cosmic puberty? The Higgs field. Here's how it worked in the hot, dense early universe. In the first trillionth of a second after the Big Bang, temperatures were so high that the electromagnetic force and the weak nuclear force were indistinguishable. They were one unified electroweak force, mediated by 4 massless force carriers, photons and something like W and Z boson precursors. As the universe expanded and cooled, it crossed a critical temperature threshold. Think of it like water cooling down. At 100 C, it's symmetric steam, all molecules zipping freely. Below 0 C, it becomes ice, a less symmetric state where molecules lock into a crystal lattice. Similarly, as the universe cooled, the Higgs field underwent a phase transition. Instead of being zero everywhere, it suddenly condensed, filling all of space with a non-zero value. This broke the perfect symmetry between the EM and weak forces. This interaction with the newly active Higgs field had a dramatic effect on 3 of the 4 force carriers. They started interacting strongly with the Higgs field, experiencing massive drag. They became heavy. These are the W+, W, and Z bosons we know. The 4th carrier, however, didn't interact with the Higgs field at all. It remained massless. That's the photon. The once identical twins diverged. The photon, massless and fast, responsible for long-range EM forces. The W and Z, heavy and slow, responsible for the short-range weak force, radioactivity, nuclear fusion in stars. The Higgs boson itself is a direct remnant of this epochal event. It's the ripple in the Higgs field that was this symmetry-breaking process. By studying it, we're not just studying a particle. We're studying a fossil from the moment the universe's forces took on their distinct identities. The discovery confirmed this entire grand narrative of unification and symmetry breaking. Nobel Prize territory number 3. It gave us experimental proof of how the fundamental forces evolved as the universe cooled. Finding the Higgs boson wasn't just about understanding the universe now. It opened a direct window to the universe then, a fraction of a second after the Big Bang. How? We mentioned the Higgs field condensing as the universe cooled. This phase transition was a critical event in cosmic history, as significant as water freezing or boiling. The properties of this transition, how sudden it was, how much energy was released, how it unfolded, shaped the subsequent evolution of the universe. Did it happen smoothly, or was it a violent, first-order phase transition, like supercooled water suddenly flash freezing? The type of transition could have implications for the distribution of matter, the formation of cosmic structures, and even the matter-antimatter asymmetry. The Higgs boson is our primary probe into this ancient event. Its mass, 125 giga-electron-volt, is a crucial number. It tells us about the strength of the Higgs field and how it interacts with itself. How often does it decay into different particles? Does it couple to other particles exactly as predicted by the simplest standard model? Or are there tiny deviations? These measurements are incredibly precise. Even a minuscule discrepancy could be a clue pointing to new physics operating at those ultra-high energies. It's like analyzing the chemical composition and crystal structure of an ancient piece of ice. It tells us about the conditions when it froze billions of years ago. By scrutinizing the Higgs boson, we're effectively analyzing the frozen state of the Higgs field transition, learning about the physics that govern the universe in its very first instance. The LHC isn't just a particle collider. It's the most powerful time machine ever built, and the Higgs boson is its most precious relic. While the Higgs boson's discovery crowned the standard model, it simultaneously became the most powerful tool we have to look beyond it. Why? Because the standard model, as triumphant as it is almost certainly not the final word. It leaves huge questions unanswered: dark matter, dark energy, gravity, matter, antimatter imbalance. The Higgs boson is uniquely positioned to be a sensitive probe for new physics. The measured mass of the Higgs boson sits in a fascinatingly precarious position. Within the pure standard model, this mass is surprisingly stable against quantum fluctuations. almost too stable. It sits right on a knife edge, without some additional stabilizing influence from physics beyond the standard model. Many theorists argue the Higgs mass should naturally be driven to a much, much higher value by quantum effects, closer to the Planck scale, the energy scale of quantum gravity, 10 to power 19 giga-electron-volt, which would make the Higgs boson far too heavy for the LHC to produce. The fact that it's only 125 giga-electron-volt suggests there might be new particles or forces out there, just beyond our current reach, acting as counterweights to keep the Higgs mass light. It's like finding a pencil perfectly balanced on its tip. It suggests hidden strings or magnets are at play. One leading candidate theory is supersymmetry. It proposes that every known particle has a heavier superpartner, e.g., electrons have selectrons, quarks have squarks, photons have photinos. These superpartners could provide the perfect counterbalance to stabilize the Higgs mass. While we haven't found these superpartners yet, they must be heavier than current LHC limits. The precise measurement of Higgs properties, how it decays, how it interacts with known particles like the top quark, could reveal subtle deviations from standard model predictions, hinting indirectly at Susie's presence. The Higgs could be a composite particle, made of even smaller things. It could be connected to theories involving extra dimensions of space. It might interact with dark matter particles. The Higgs boson is like a new, incredibly sensitive instrument. By measuring its properties with ever greater precision at the LHC and future colliders, we are conducting experiments that could reveal fingerprints of these hidden realms. Does the Higgs decay slightly more often into certain particles than expected? Does it interact slightly differently with the top quark? These tiny anomalies could be the first cracks in the standard model facade, leading us to the next, deeper layer of reality. The Higgs boson, the capstone of the old theory, is the master key unlocking the door to the new one.
So, why the monumental deal? Why the Nobel tears? It's the sheer breathtaking scope of what this one ghostly particle represents. It's the intellectual triumph, the validation of decades of human curiosity, ingenuity, and the power of mathematical beauty. Theorists dared to dream of a field filling the void, and experimentalists built a cathedral underground to find its ripple. They succeeded. It's the cosmic revelation. Understanding that the solid ground beneath our feet, the air in our lungs, the screen glowing before your eyes, all trace their material existence back to an invisible cosmic molasses we move through every second. The Higgs field is the silent sculptor, turning energy into substance, chaos into structure. Without it, the universe would be a fleeting, formless flash. No stars to wish upon, no planets to call home, no life to ask why. It's the historical echo, capturing a direct signal from the universe's first trillionth of a second, witnessing the moment electromagnetism and the weak force went their separate ways, shaping the forces that govern stars and atoms. And it's the daring invitation. The Higgs boson, sitting so perfectly, so precariously at 125 giga-electron-volt, is our brightest beacon pointing towards the vast unknown. It whispers that the standard model, magnificent as it is just the first chapter. Dark matter, dark energy, quantum gravity. The answers lie ahead, and the Higgs is our guide. Finding the Higgs boson didn't just answer an old question. It fundamentally changed our relationship with the universe. We didn't just discover a particle. We discovered the mechanism that allows us, and everything we know, to exist. We proved that we can ask the deepest questions about the fabric of reality and, through ingenuity and collaboration, find the answers. It transformed us from passive observers into active decoders of the cosmic code, holding in our hands, or rather, in our 27-kilometer tunnels, the key to understanding why there is something rather than nothing. That, my friend, is more than monumental. That is the sound of humanity understanding its own place in the grand Higgs-anchored scheme of things. And the journey, fueled by that discovery, has only just begun. The cosmic campfire burns brighter than ever, illuminating paths into the unknown. Ah, the God particle. That nickname. It's like that one slightly embarrassing, overly dramatic uncle at a family gathering who means well, but always steals the spotlight with a tall tale. It's catchy. It's memorable. It certainly grabs headlines. And it makes most physicists want to gently, or sometimes not so gently, facepalm. Let's unpack this nickname saga, why it's stuck, and why the folks who actually study the Higgs boson find it about as scientifically accurate as calling a toaster the God appliance because it makes your bread turn golden. Our story starts with Leon Lederman, a brilliant physicist, Nobel laureate, and a man with a flair for the dramatic and a healthy dose of scientist's sarcasm. In the early 1990s, he was writing a popular science book about the then ongoing, incredibly challenging, and monumentally expensive quest to find the Higgs boson. Decades had passed since its prediction. Experiments at CERN's previous giant collider, LEP, had hinted but found nothing conclusive. Plans for the LHC were underway, facing immense technical hurdles and eye-watering costs. The Higgs boson was the ultimate tease, theoretically essential, frustratingly absent. Letterman, capturing the collective exasperation of the physics community, reportedly wanted to title his book, The Goddamn Particle. Think about it. Goddamn perfectly encapsulated the feeling. It was elusive. It was expensive. It was holding up the completion of their beautiful theory. It was driving them nuts. It was the particle equivalent of that one missing puzzle piece you know is hiding under the sofa, mocking you. Goddamn particle was raw, honest, and hilariously relatable to anyone who'd ever wrestled with a stubborn problem. But publishers are in the business of selling books, not venting scientific frustration. Goddamn particle landing on bookstore shelves, too spicy, too risky. They needed something cleaner, something grander, something that would make people stop and go, "Ooh, what's that?" So they lobbed off the damn. Just like that, the God particle was born. And boy, did it land. The media loved it. It was mysterious. It sounded profound, almost mystical. It hinted at ultimate answers, at touching the divine fabric of reality. Newspapers, magazines, documentaries, they all latched onto the God particle. It became the go-to shorthand, far eclipsing the clunkier, more technical Higgs boson, or even just Higgs. Lederman's book became a bestseller, and the nickname embedded itself in popular culture like gum on a hot sidewalk. Mission accomplished for the publishers, right? Here's where the friction starts. While the public embraced the cosmic grandeur of the God particle, physicists winced. Why? It's not just snobbery. It's about accuracy and the very nature of scientific understanding. Let's break down their main gripes. The divine misconception. This is the big one. The nickname unavoidably, powerfully suggests a connection to religion, theology, or some kind of supernatural creator. It implies the Higgs boson is somehow responsible for the creation of the universe, or that it imbues particles with a divine spark of existence. This is completely wrong. The Higgs boson and the Higgs field it represents is a fundamental part of the universe as described by natural laws and physics. It's not mystical, it's mechanical. It operates according to the rules of quantum field theory and the Standard Model. Rules we can test, measure, and understand through mathematics and experimentation. Finding the Higgs boson wasn't like discovering the fingerprint of God. It was like finally identifying the specific component in a vast, complex cosmic engine that explains why one particular gear, mass, functions the way it does. Calling it the God particle fundamentally misrepresents its nature, dragging it into a realm of meaning that science doesn't and can't address. It's like calling gravity the God pull because it holds planets in orbit. Impressive? Absolutely. Divine? Nope, just physics. The final answer. Fallacy. The God particle nickname carries an aura of finality, of the ultimate answer. It suggests that discovering the Higgs boson explained everything, solved all the mysteries of the universe. Nothing could be further from the truth. While the Higgs discovery was a monumental triumph that completed the Standard Model and explained the origin of elementary particle mass, it simultaneously highlighted how much we don't know. Dark matter. We know about 85% of the matter in the universe is completely invisible, doesn't interact with light, and doesn't seem to be made of any particles in the Standard Model. The Higgs boson has nothing to do with explaining this colossal mystery. What is this stuff? We haven't a clue, and it dwarfs the normal matter the Higgs helps explain. Dark energy. Even weirder, the universe's expansion is accelerating, driven by some unknown energy permeating space. The Higgs field is uniform and gives particles mass, but it doesn't explain this repulsive force, pushing galaxies apart faster and faster. Dark energy is about 68% of the universe's total energy budget. The Higgs boson is silent on this. Gravity. The Standard Model beautifully describes three fundamental forces: electromagnetism, strong, weak. Gravity, the force we feel every day, is described by Einstein's general relativity, but we have no idea how to make it fit into the quantum world described by the Standard Model. The Higgs boson doesn't help unify gravity with the other forces. That's perhaps the biggest unsolved problem in physics. Matter versus antimatter. The Big Bang should have created equal amounts of matter and antimatter, which annihilate each other on contact. Yet, we live in a universe made almost entirely of matter. Why? Some tiny asymmetry must have favored matter. The Standard Model, even with the Higgs, doesn't provide a big enough explanation. Where did all the antimatter go? Neutrino mass. The Higgs explains why neutrinos have mass, but it doesn't explain why their masses are so incredibly tiny compared to other particles. That's another puzzle. Beyond the Standard Model, is the Higgs boson exactly as predicted? Are there more Higgs bosons? Does it connect to theories like supersymmetry or string theory? The Higgs isn't the end. It's a powerful new tool to probe beyond our current understanding. Calling the Higgs the God particle is like discovering the engine in your car and declaring you now understand everything about traffic jams, global transportation networks, and the meaning of road trips. You've understood a vital component, but the bigger picture is vastly more complex. It oversells the Higgs's role and disrespects the depth of the remaining cosmic mysteries, overshadowing the human effort and the real mechanism. The nickname subtly shifts the credit away from where it belongs. It sounds like this particle is God, or God's particle, but the real story is one of human ingenuity, collaboration, and decades of relentless effort. It's the story of Peter Higgs, Francois Engler, Robert Brute, Gerald Guralnick, C.R. Hagen, and Tom Kibble wrestling with complex equations in the 1960s. It's the story of thousands of engineers engineers, technicians, and scientists from over 100 countries designing, building, and operating the LHC and its detectors over decades. It's the story of theorists refining predictions and experimentalists sifting through mountains of data. Calling it the Higgs Boson directly honors the people and the mechanism, the Higgs mechanism field that underpins it. The God particle erases that human story and the specific physical concept, replacing it with a vague, quasi-religious label. It turns a hard-won scientific triumph into a soundbite.
The perpetual headache. Why the nickname persists. Despite physicists' protests, the God particle endures. Why? It's short, dramatic, and unforgettable. Higgs boson sounds technical and dry in comparison. It taps into a deep human fascination with the ultimate, the divine, the foundational. It promises cosmic significance, even if it misrepresents it. Journalists and documentary makers know it grabs attention. It's a guaranteed headline. Using the technically correct term often feels like it lacks punch for a general audience. Let's be honest, for people outside physics, saying, "I'm reading about the God particle," sounds way cooler than, "I'm reading about the Higgs boson and spontaneous symmetry breaking in the electroweak sector." Living with the nickname, a scientist's sigh. So, how do physicists cope? Mostly with resigned sighs, patient explanations, and sometimes a bit of eye-rolling. When someone at a party asks, "Oh, you work in physics? Tell me about the God particle," they take a deep breath. They might start with, "Well, we actually call it the Higgs boson," and then launch into a simplified explanation of the field and its role in mass, carefully steering the conversation away from theology and towards the actual, equally mind-blowing science. They understand why the nickname exists. They appreciate Lederman's original, frustrated sentiment. They even grudgingly admit that it has helped spark public interest in fundamental physics. But they also know it's a double-edged sword. It brings people in with a potentially misleading promise, and it can create a barrier to understanding the actual significance, which is profound enough without needing divine hyperbole. The true wonder of the Higgs boson isn't captured by a flashy nickname implying divine intervention. The real awe lies in the human story. Theorists dreamed up this particle and its field based on the internal consistency and beauty of their equations decades before we could see it. The scale of human collaboration. The LHC is arguably humanity's largest and most complex scientific experiment, a testament to what we can achieve when we work together across borders. The engineering audacity, building a 27-kilometer super-cold superconducting ring to recreate the universe's infancy billions of times per second. That's pure, jaw-dropping human ingenuity. The persistence, decades of setbacks, funding battles, technical nightmares, and data analysis marathons, all driven by insatiable curiosity. The profound natural explanation. Discovering that mass, the property that makes you, me, planets, and stars tangible, arises from an invisible cosmic field we move through, a field whose signature ripple we finally captured. That's a deeply humbling and magnificent revelation about the fabric of reality itself, grounded in natural law, not mysticism. So, the next time you hear the God particle, smile knowingly. Remember Leon Lederman's exasperated goddamn particle and the publisher's quick edit. Remember the physicists patiently explaining over and over that it's really about a field and mass. And remember the actual wonder. That curious, determined, collaborative apes on a tiny planet built a time machine to glimpse a fundamental process from the universe's first moments, revealing why they have substance at all. That's the real miracle.
and it needs no divine nickname to be utterly astonishing. The Higgs boson, in all its complex, hard-won glory, is impressive enough just being itself. Let's call it by its name. Now, coming towards the end of this video, be clear that the discovery in 2012 wasn't an end. It was a magnificent beginning. The LHC continues to smash protons, collecting billions more collisions. Why? To study the Higgs boson with incredible precision. How often does it decay into different particles? Does it interact with other particles exactly as predicted? Are there any tiny deviations that could hint at new particles or forces? Is there only one type of Higgs boson? Or could there be more, as some theories suggest? Does the Higgs boson interact with dark matter? The Higgs boson is now our newest, most powerful microscope for probing the deepest layers of reality. Every subtle measurement tells us more about the fabric of the universe. It's like finally finding a legendary ancient key. Now we have to figure out all the locks it might open. So the next time you feel the reassuring weight of a cup in your hand or the solid ground beneath your feet, remember the invisible ocean of the Higgs field you're moving through. Remember the tiny, fleeting ripples within it, the Higgs bosons, that are the signature of the mechanism granting that solidity. It's a humbling thought that our quest to understand the tiniest building blocks of existence has revealed the reason we don't simply evaporate into the void. From the quantum frenzy within atoms to the majestic swirl of galaxies, the Higgs field is the silent choreographer, setting the stage for mass, for structure, for us. The discovery of the Higgs boson was a testament to human curiosity, collaboration, and sheer engineering audacity. It showed us that even the universe's deepest secrets, hidden since its first moments, aren't beyond our reach. We built a time machine, looked back 13.8 billion years, and caught a glimpse of the fundamental process that allows the universe to be more than just light. We found the spark in the cosmic campfire that makes warmth and substance, and ultimately the story of everything, possible. And that truly is a wonder worth celebrating. Here comes the end of today's story. If you have learned something new, then please like this video, subscribe to our channel, and recommend it to your curious friends. Good night. Have a deep sleep.